Hello. In this lecture, we're going to look at Laplace transforms and how to use Laplace transforms to solve circuits problems. So before we start, let's remind ourselves the Laplace transform pairs, the typical Laplace transform pairs that are likely to be encountered in circuits problems. Um, and these are basically the step functions, the impulse, exponentials, and either everlasting sinusoids and also decaying sinusoids. So these are typically the ones that you come across when you solve circuits problems, with few exceptions, but these are the main ones. So these you will find in most Laplace transform tables. So these are called Laplace transform pairs because the time domain function x of t goes with the frequency domain or Laplace domain function x of s. Along with this, there are a number of Laplace transform properties, and there are quite a few Laplace transform properties. But just to start with, the most important ones are the scaling property, the addition subtraction property, and the differentiation property. So these are already been outlined, and again, you will find this typically in most coverage of Laplace transforms, typically in a course of differential equations. But basically, the scaling property has to do with the fact that if you scale the time function, you scale the Laplace transform by the same level, same amount, same factor. If you can write a function as two functions, or if you have two functions, let's say x1, x2, that are just separate, and you know their Laplace transforms, and if you happen to make a new function from their sum or difference, the Laplace transform of the sum of the difference is the sum of the sum or the difference of the Laplace transforms. Pretty obvious. And the differentiation property, of course, is a little bit different, but if you neglect the initial condition, which is x0 minus, if you have a Laplace transform of a function, then the derivative has a Laplace transform that's s times the original Laplace transform. So basically, taking a derivative of a function multiplies the Laplace transform by a factor of s. So each derivative gives you another factor of s. So a second derivative would involve s squared x of s with some factors at the end. So the x0 minus, which is the initial condition of the time function x of t, they will come in. They will become important later on, but for now, we can just ignore it if we're gonna initially assume that the systems are starting at rest, or what we call zero initial conditions. Okay, so let's start with some other fundamentals before we jump into examples or fundamentals. Is that each circuit element can be replaced by its Laplace transform equivalent when we solve problems. So instead of finding the differential equations and taking the Laplace transform of the differential equation, we can just take the circuit, take the Laplace transform equivalent of that circuit, and then the circuit becomes an impedance circuit, like a phasor circuit with impedances in ohms, and it's basically solving a DC circuit. So here are the circuit elements and their equivalent Laplace transforms. So pause and take a look at that in a little bit. And as you see, for a resistor, there's really not a difference because the impedance of a resistor, ZR, is the resistance itself. But for the capacitor and inductor, the IV relationships have derivatives. And it turns out that if we go to the frequency domain, the Laplace domain, we can still have an Ohm's law relationship, V equals I times something, and that something is the impedance. So for inductor, it's SL, and for a capacitor, it's 1 over SC. Again, this is very similar to the frequency domain frequency domain representation of phasor domain impedance, which is j omega L for the inductor and 1 over j omega C for the capacitor. So these are things that we've seen before, and they're really not that different. but instead of j omega, we're using s. You can kind of think about it that way. Although that's a little bit of a too much of a there could be too much of a jump. But anyway, you can just think about it that way for now. All right. So having said all this, let's take a look at some circuits that we may have considered earlier by using switches and so forth to basically get first order transients. For example, let's look at an impulse response of an RC circuit. Now, impulse we haven't seen, but as far as we're concerned, it's another function. It's a discontinuous function. It's a singularity function. So we may ask, if we excite an RC circuit with zero initial conditions with an impulse, what's the response? What's VCOT? So how does A delta T kind of look like? Well, again, it's a function that we denote this way, that occurs at time equals 0. And the A represents the area of this function, and we typically put it in parentheses to note that it's not the amplitude, it's actually the area. This impulse theoretically has zero width in time and infinite amplitude, in this case volts, because this A delta T is actually the input voltage. So units of A might not be what you think. Okay, it's actually not volts, because that will be the amplitude of the voltage, right? A is the area. So if you think about it that way, area on a volt versus time curve, that green curve, well, that really has to be volts times seconds, right? That's the only way you can have an area. So A, the reason I chose the letter A, because it's an area. So that represents the area of that function, in quotes. It's not really a function, but that entity, you could say. Okay, now once we have this definition and we have the initial condition 0, then we can work the differential equations. But typically what we do is we just take the circuit and we draw the Laplace transform equivalent of the circuit. So the resistance becomes our resistance, because it's the impedance of a resistance is in ohms, right? So in this blue circuit, all elements have to be impedances. So the capacitance becomes 1 over SC. The voltage VC of t, this is like our X of t, right? Becomes X of S. So we write capital V C of S. So that's not the VCT that we want, but the VCS is its Laplace transform. Okay, and then we have a voltage source whose value is a Laplace transform of A delta t. Now we know that the Laplace transform of delta t is 1, and scaling it by A with the scale the Laplace transform by A. So if you look up here, delta t, the Laplace transform is 1. So A times delta t, Laplace transform will be just A. So the Laplace transform here is simply A. And that's it. This blue circuit now represents the Laplace transform equivalent of the original circuit. So we can maybe put a little notation here that we Laplace transform the circuit. And now the nice thing about this blue circuit is that everything is pretty much is in ohms. 1 over SC is in ohms, R is in ohms. A looks like a DC voltage source basically, which it is not, but we can treat it that way. And VCS is the voltage across the capacitance. So to solve for VCS, we can just use voltage division. Instead of resistances, we have impedances. So again, this is very similar to using the impedance calculations that we did in phasor analysis, right, where we use j omega. So this is very similar. So we will just use voltage division. For example, you may use some other techniques. So VCS would be the impedance across which it's being measured divided by the sum of the impedances. Remember, 1 over SC is in ohms, so we can add R plus 1 over SC times the applied voltage, A. And there it is, that's VCS. Now, of course, we have to put VCS in a certain form to do the inverse operation, because ultimately we're interested in VCT, not VCS. So we have to go back, and the way we go back is we do that by the inverse Laplace transform, which we typically do by performing partial fraction expansion. So what that means is we try to write what we want, in this case VCS, by a sum of recognizable terms that appear on the right side of this table, right? So if we recognize 1 over s on the right side, that means time function must be u of t. If we recognize some multiple of 1 over s, there's some multiple of u of t on the left side. So it's basically doing kind of like pattern matching, or just matching the right side of the Laplace transform table, the pairs, to something here, and they have to be recognizable. So in this case, we do a little bit of algebra. So let's start to write the VC of s here. Sorry, wrong pen. So VC of s, if we multiply in the fraction top and bottom by SC, we'll get 1 over 1 plus SRC, or SRC plus 1, doesn't matter, times A. And then, of course, we see that in the Laplace transform table. I won't go back, but I'll just tell you. Then in the Laplace transform table, we have terms like 1 over s plus A, lowercase a. So let me just do this, and you'll see why in a second. Okay, so I just divide top and bottom by RC, and I get this. And of course, with a factor A, we can write that over here. So if we compare that to what we see in the Laplace transform table, you'll see that in the Laplace transform table, we have something like this. I'll just write it here for convenience. When you have something like s plus a, this corresponds to e to the minus at u of t. U of t is a function that basically zeroes out anything less than 0. So e to the minus at ut is a function that's 0 for t less than 0, and it's just e to the minus at for t greater than 0. So it's kind of like a 0, 1 kind of a function. Anyway, if I see 1 over s plus a, its inverse Laplace transform is e to the minus at ut. So here, I don't exactly have that, but I have a scaled version of it. So basically, if I have some scaling factor k, then you have a scaling factor here. Why? Because the Laplace transform has that multiplicity property, where multiplying the x of t means multiplying the x of s. It's a linear transform. We expect it. So here, we identify this right here as our k, and this right here as our a. Therefore, taking the inverse Laplace transform, right, in other words, VC of t, is simply k e to the minus at ut. In other words, we have a over rc e to the minus lowercase a is 1 over rc, so it's 1 over rc times t, or t over rc, ut. And that's it. That's our solution. That's our inverse Laplace transform. Now, what you have to note here is that the function VCT, right? The amplitude is this, right? This is the value that's sitting up front. So in other words, if I had to draw this function, right? If I had to draw this function, let's just do that for now, right? Here's the input. Input was impulse. We drew it out already. Let's just do it again. So here's our Vn. Had a area A. And the response that we're getting, this VCT that I just solved for, that looks like this, right? So here's time. First of all, since we have u of t right here, it means that this function is 0 for t less than 0. So if this is my 0, I'm going to have 0 all the way up to here. So actually, the voltage, initial voltage, VC at 0 minus is actually 0 volts as required. But once I have U of t, with t greater than 0, right, it's going to jump. So this function will jump. So VC will change instantaneously, and that value right there is A over RC. And then it'll just decay exponentially like this. Not a great picture, but gives you the point. But the point that I want to make here is that this right here, A over RC, that has to have the unit of volts. And it does. The reason is because, remember, A, right, A has the units of what? Remember, it's an area. And remember, this is our V and T. And A is an area. So A has the units of volts times seconds. And you should remember from what we did before that RC is a time constant, has units of seconds. So A over RC, right, has the unit of volts as required. So that makes sense. So these are just little sketches. They're not, these are not very artistic, but hopefully the point is getting across that this is a time function, and you have the instantaneous jump, right? So what you have here is that our initial condition, remember, was this. And right after the switch is closed, right after the switching happens, VC 0 plus, right, you have an instantaneous jump to A over RC volts. And then that'll just decay exponentially with time constant RC. Right? So the time constant here is RC. So this is an impulse response of an RC circuit, and many more complicated RC circuits can be analyzed in a very similar way by some transformations and some simplifications, but this is the basic stuff, or this is the basic impulse response of a typical RC circuit. Okay. So again, this is our beginning, and we just went through the analysis. Okay. Now let's take a numerical example. Although a numerical example maybe might not teach you much more at this point, but it's good to have some practice. Also, the reason I show this part with variables is because if you simply have numbers, it's very easy to get lackadaisical with the units. And you might not realize that the units that you're using are not what you think they are. Okay, so let's do an example. I put a little example here. So this is just like a similar circuit, but not exactly the same. But the point is that the input here is an impulse. So the input here is 9 delta t. So now we know what that 9 is. In this case, a voltage source. That means that, if you have to, again, make a little picture here, this is time. Our input is like this, right? And the area is 9, and that 9 is volt seconds. The units is volt seconds. It's not volts. It's not unitless. It's actually volt seconds. Okay, so just keep that in mind. That's how our input looks like. Again, we're interested in the output voltage, VCT, or the capacitor voltage. Take it to be whatever you like. But the initial condition, again, is 0. So in this series of lectures, we're just taking all initial conditions on the capacitors and inductors to be 0. System is always at rest, just to make it a little simple. All right, so now we can jump into the circuit and try to analyze it right away, or write a bunch of equations, or take the Laplace transform equivalent right away. You could do that. Nothing wrong with that. But either in the Laplace domain circuit or this circuit, you can notice that we have some resistive circuits, and so you can maybe take some simplifications here. You can maybe do some source transformation or something like that. You can do them at any point. For example, let's take the Laplace transform first and then do some simplification before we start analyzing it. All right, so let's do the Laplace transform circuit first. Again, we're going to go from here to the Laplace transform equivalent. Okay, we learned that, of course, the Laplace transform of 9 delta t is simply 9. Resistors are just resistors. There's really nothing to do with them. They're very simple. The capacitor, the impedance of a capacitor is 1 over SC, and the C is 1 over 10, so this becomes 10 over S, and this becomes our VC of S. So we already set up our Laplace transform circuit. But at this point, instead of writing node equations or something like that, I would say, let's just simplify the circuit first. In fact, simplify the circuit to the left of the capacitor. First starting with 9 and the 3. 9 volt source, or 9 volt second source, you could say, and the 3 ohm resistor, right? So we can source transform that. Let's do that. So if we do that, then that goes to this circuit right here, right? So 9 over 3 becomes a current source of value 3. 3 ohm becomes is in parallel, and then we get the 6 ohm, and of course we have 10 over S here. And I'm trying to do these things live, and so I have not prepared this. I'm just doing it live, so you see how it's done in real time. That way, maybe I might even introduce some errors into this, and then you can mark some points off on my performance. But anyway, this is how the circuit structure looks like if you source transform this section right here. Okay, and now of course we have some simplifications because we can do 3 parallel 6, right? So we've seen this so many times, but again, 3 parallel 6 is 2 ohms. And of course now 2 ohms would parallel with 3, another source transformation. So we have the 2 ohm, which is the equivalent, comes up here again. We have our capacitor, which is 10 over S, comes over here, and this is VC of S, right? And then we have a voltage source whose value is 3 times 2 becomes 6, and there you are. And the reason I did that is because now this circuit that I just drew, this is actually the same structure, right? It's the same basic structure as we did before, like this, right? I mean, the only difference is the values of A, R, and C. That's the only difference in the circuit that I have right now. So, not that different. One capacitor. So we expect an exponential response. Very similar. But let's just write down the expression for VCS anyway. Voltage division, right? That's what I would do. And then, so VCS equals 10 over S divided by 2 plus 10 over S times the voltage source, 6, right? That's voltage division for you. And let's just continue down here. So now VCS, if you multiply top and bottom of the fraction by S, you have 10 divided by 2S plus 10, again times 6. If you divide top and bottom of the fraction by 2, then you have something like this. So I'm trying not to skip too many steps here so you see everything. Okay, so this is not, there's no circuit theory here, this is just math, right? And now what we have is we have 30 over S plus 5. Again, this is very much similar to the expression we had before, right? Where we had this. I'll just write it from memory because it's pretty simple. K to the minus AT, UT, right? this is a Laplace transform pair of k over s plus a. Here k is 30 and a is 5. So that means that when you do the inverse Laplace transform, VCT is going to be 30 e to the minus 5t ut volts, right? So this is in volts. Just like before, this function that I wrote down before, I didn't want to write too many variables here, but this is obviously in volts because A over RC was in volts. Same thing down here, right? So this 30 e to the minus 5t exists over all time, but if you multiply by ut, you basically zero out the portion that's less than t equals 0. So anyway, the input looks like this, right? Remember, it was v in t was actually 9 delta t, if you remember in the original problem. So this is going to have an area of 9, like this. Sorry, just rewrite that in the right way. So this is going to be 9, and this is times 0. And then the time function for v out, so this is v out of t, is going to look like this, right? It's going to jump. So this is your 30 volts. But the important thing to understand is that the initial condition, right before the delta function was applied, the initial capacitor voltage was 0, whereas VC0 plus, right after the delta function, it jumped instantaneously to 30 volts. And the only way to change capacitor voltage instantaneously, like in this case, is by the presence of an impulse, right? So if you have any other function, you have like a step function, a ramp function, a sinusoid, the capacitor voltage cannot change instantaneously. So whatever your initial condition is, VC0 minus, it's got to be the same. VC0 plus got to be the same. But if you have an impulse in your circuit, like in this case, the capacitor voltage may jump instantaneously. Of course, all other variables, except for the inductor current, may jump instantaneously in any case. But the capacitor voltage and inductor current, the state variables, may only have instantaneous jumps if there's an impulse in the circuit, right? And in this case, there was, and therefore there's a jump, right? All right, so that's good. And, you know, there's a lot of problems that we can handle with this kind of impulse now, right? So you know how to work with the impulse, at least by itself. Of course, when you have more elements, more functions, or more sources, things get a little more complicated, but this is kind of the way it goes. All right, so let's move to the next item, which is, again, just looking at the RC circuit, because these are fundamental circuits. You have to know the response of these, I want to say, by heart. You have to know what to expect with these. And then, like, the next one is the step response of a RC circuit, right? Step response. So now, instead of applying an impulse, we're applying a step. So the input right here, V in of t, goes like this, right? So initially it's at 0 volts, and then it jumps to V0 volts, like this. And that happens at t equals 0. So in this case, as I was just mentioning, even though there's a instantaneous jump in the input, it'll turn out that the capacitor voltage will not jump instantaneously. In fact, in this case, we're given VC0 minus is equal to 0 volts. We will see that VC0 plus should also be 0 volts. So the capacitor voltage, in this case, will be continuous. All right? But first, let's look at this problem and then see how it'll solve, at least with variables. And then when you come to numerical examples, it'll be fairly straightforward. Again, the thing to remember is that since this is a first order circuit, we expect exponentials, And in this case, it's a step input. There might be a step, right? But that's it. We're not going to get like a sinusoidal response out of a first order circuit. We're not going to get that. First order circuit, so the response is going to be first order at most, right? But you might have a step in there in this case as well, you'll see. All right, so let's just do the same thing we did before. Let's take the Laplace transform of the entire circuit, right? Again, when we take the Laplace transform circuit has the same structure, right? So it's going to be R, it's going to be 1 over SC, it's going to be, so these are all the same as before. We can just copy here. And the only difference is the Laplace transform of V0 u of t. Now, if you go back to the first page, you'll see that the Laplace transform of 1 over S, okay, is u of t. So V0 u of t is V0 over S. That's all there is to it. That's the only difference in this circuit versus the circuit that we did for the impulse response of an RC circuit. So here we have it, and then that's pretty much it. And we solve it exactly the same way too. So I won't belabor all that stuff, but I'll just say again, voltage division, right? If you do voltage division, you'll get that Vc of S is a fraction of what you apply. And that fraction is given by the ratio of the resistors that are in series, right? Well, these are not resistors, in fact, these are impedances. R is a resistor, it's also an impedance. 1 over SC is the impedance. Remember, 1 over SC is in ohms, so is R. Therefore, we can do R plus 1 over SC. I'm repeating it, but it's important to know that that's true. You can't do R plus C, okay? You can't do R plus 1 over C. Can't do those. Units don't match, it's wrong. You cannot add apples and oranges, okay? But you can add impedances, and that's what we're doing right here, okay? And in fact, we're just doing almost like a resistive circuit. The only thing we're carrying along is that S term, okay? All right, now, again, let's just do the thing that we did before. Let's multiply top and bottom by SC in the fraction to get rid of the fractions. All the fraction, right? So you have 1 over SRC plus 1 times V0 over S. And let's divide top and the bottom of the fraction by RC. So you have basically 1 over RC divided by S plus 1 over RC. And the reason we're doing this is so that we can put the expression for VCS as a product of things that appear on the right side of the Laplace transform, right? Because after all, we're going to do everything by partial fraction expansion. That's the way we're going to go back to VC of t. Once again, we're not interested in VC of S per se. VC of S happens to be just like a intermediate point. We really want VCT, so we have to go back from VCS to VCT, and we do that by basically partial fraction expansion. And so here, when you see terms like S plus 1 over RC and S like this, I mean, the bottom there looks like S plus A, and then we have just S, and you have a product of these two terms. So if you go back to the Laplace transform table, I mean, we basically have a term that is sort of maybe some kind of multiple of u of t, right? And then 1 over S plus A, it's a multiple of maybe e to the minus at ut. So we're going to have an exponential and a step. That's what it kind of looks like. What the ratios are, what the factors are, what the coefficients are, we don't know yet, but that's what partial fraction expansion gives you, right? In other words, partial fraction expansion says we should be able to write this as A over S, for example, plus B over S plus 1 over RC. Because if we have the A and the B, then the Laplace transform is easy, right? Because the Laplace transform then would be, this is the inverse Laplace transform, you would have A ut plus B e to the minus 1 over RCT ut, right? If I find A and B, my problem is solved because this will be my VCT. So what I got to do is find A and B. And the way we find A and B is by using partial fraction expansion method, where A and B are determined by a number of methods. There's a cover-up method, there's a residue method, there's different ways, right? Cover-up method and the residue method, I guess, are the same, but you can also match the coefficients. Let's match the coefficients. Again, I don't care which way you do it, but if we take this, for example, and take it over here, right? One way we could solve for A and B is after we have written the blue portion as the sum of the two S and the S plus 1 over C factors, is we can combine the A and B factors again like this. You could say, for example, I can get a common denominator like this, right? And then I have to multiply A by S plus 1 over RC and B by S. And now I'm in business, because now I should have this and this, they should be the same. Well, they have the same denominators. That means their numerators should be the same, right? So what are the numerators? Well, on the right side, I have AS and BS. So for example, I have A plus B times S. That will be the coefficient of S. And I have a constant term, A over RC. On the left side, I have V0 over RC. That's my constant term. And then, of course, there is no S term, so the S term is 0. So what that means is that if the S term is 0 on the left side, this has to be 0 as well. And on the left side, if the constant term is V0 over RC, then this has to be V0 over RC. Right? And you can see that from the last expression, V0 over RC equals A over RC. This means that A equals V0. And then from A plus B equals 0, it means that B equals minus A. And since I know A, B must be minus V0. Then I found my solution, right? Because VCT is sitting right here. Because once I have my form, I know the form of my solution. I just don't know my coefficients. Now I know my coefficients A and B, and I simply pull them in and write it down, right? So I just say VCT is equal to A UT, which is V0 UT, and B is minus V0, e to the minus T over RC, or minus 1 over RC times T, take your choice, U of T. And that's it. And sometimes we write this as V0 times 1 minus e to the minus T over RC UT. So the step response, right? I mean, if our input was like this, right? So this is our V in of T. Let me just draw this again. Looks like this, right? And this is my time function, or time axis. This is 0. Here's my time axis again. Okay, this time I'm going to draw Vc of t. Vc of t is 0 up to here, because I'm multiplied by ut anyway. But what's important is that Vc 0 minus is equal to 0 volts. Right before the step hits, right there. And after the step hits, of course, my function goes like this. And it approaches V0 as time goes to infinity, because the exponential goes to 0. But what's also important is that Vc0 plus is also 0 volts, because if you go to this function right here and put in t equals 0, you'll get V0, 1 minus 1, which is 0. So voltage is continuous. Okay? So this is the step response, a basic step response on an RC circuit. let's do an example, right? And then let's make the example maybe a little bit different in the sense that let's not make it look exactly like what we have here. Maybe we can put a current source, right? Because step response doesn't just mean a voltage step, it could be a current step. For example, like this. So you have two resistors and a capacitor. Again, since this is since I'm covering RC circuits, I'm having resistors and one capacitor, right? That's what I'm trying to do. And of course, we have a step input for U of t. That's a current, right? So that means that I have a current that looks like this, right? So initially it's 0 amps, and then it goes to 4 amps, and it changes at t equals 0. So that's how that looks like. Okay. Now again, we can simplify first, then take Laplace transform, simplify. But the important thing is that whenever you can, you should try to simplify at some point before you start to fully analyze a circuit. So let's take the Laplace transform first. Again, the circuit is going to look very similar, but again, for U of t, this becomes 4 over S amps, current source. This is 3 ohms, 7 ohms, 1 over 10, sorry. Let's go, this is impedance, so 10 over S. And this is VC of S. So we can do that. And then what we can do is we can maybe do a little bit of source transformation before we go on with our analysis. So what we can do is we can take, for example, this section right here and do a source transform. Now, at this point, you can go ahead and write nodal analysis equations, but you should not attempt to do those things until you feel that the circuit is simplified as much as you can. So let's just do that. Source transformation. So you get 3 ohms in series with a voltage source whose value is I times R. So it gives you 12 over S as the source. And now you have 7 here, right? This is 10 over S. This is VC of S, right? And now, oh, you see 3 plus 7 is in series. Great. 10 ohms. I'll take that. So now our circuit is like this, right? We have 12 over S, 10 ohms, and this is 10 over S ohms actually as well, and this is VC of S, and voltage division again, right? I mean, I guess we could have transformed one more time, do current division. We can do all kinds of things, but I'm just taking it back to the original circuit that we dealt with. Voltage division, right? 10 over S, 10 plus 10 over S, and then we are going to apply 12 over S, right? Simplify the circuit. The fractional part, multiply everything by S, right? And you can do it different ways, but I'm just going to do that first. Get rid of the S's, so they're going to be 10. 10S plus 10 times 12 over S. Well, at this point, in the fractional part, 10 over S, 10S plus 10, divided by S. Very simple, right? So this becomes 1 over S plus 1, and then 12 over S. So that's our starting point for VC of S, right? It's going to be something like this. 12 divided by S, S plus 1. And then partial fraction expansion of that would be something like this. And again, there are different methods of computing A and B. There's a residue method, but at this point, I'll just do the same thing that we did before. Just look at the coefficients, coefficient matching. Let's put it this way. So if I recombine these things, I have S, S plus 1, A, S plus 1, plus bs. So the matching the numerators here, we're going to match the numerators here and here, right? So on the left side, you have 0s plus 12. On the right side, you have a plus b times s plus a. So we're getting. So that means that obviously a equals 12 and a plus b must equal to 0. So b equals minus a equals minus 12. That means that VCT is, AUT, right? It's going to be AUT plus b e to the minus TUT. So just like we did before, we're going to get 12, 1 minus e to the minus TUT. So very, very similar, very, very similar. In this case, our input is a current, right? So our input was actually this. It was a current. It was I in of t, you could say. So let's go down at the bottom of the page here and just sketch it, just for our own purpose, so that we get a visual for it. Doesn't have to be perfect or anything like that. But here was I in of t. And the response, the step response, right, is like this, right? So we have 0, and then we approach 12 volts. This is our VCT. So this should give you a feel about how to do at least the simple Laplace transforms for RC circuits. First order RC circuits, impulse response and step response. I did it both symbolically and gave you some examples, and I gave you some sketching, give you a feel for how this is done. Of course, the way you get better at it is you just have to do more examples. But this is like the starting point, because typically impulse response and step response of circuits are the most fundamental responses you should know for each one of these. All right. Next time, I'll do the impulse response and the step response of an RL circuit, which is going to be very similar, but a little different. But not too different. See you next time.